Webb has shattered another cosmic record. But this time, the implications go far beyond finding something distant. The telescope just spotted galaxy MOM Z14, and its characteristics are so shocking that they're forcing scientists to question our most basic understanding of how galaxies form. Webb's 6.5-meter mirror sees red-shifted light that Hubble couldn't, letting us spot signals that began their journey over 13 billion years ago. This isn't just about breaking distance records. It's about finding a galaxy that shouldn't exist in the form we see. With a redshift of 14.44, we're seeing MOM Z14 as it was just 400 million years after the Big Bang. And what it's telling us is rewriting the textbooks on early universe formation. But the story of how astronomers first realized what they had discovered reveals how extraordinary this find truly is. The record that changed everything. Picture the moment astronomers first processed the data from Webb's near-infrared camera and realized they were staring at something that defied every prediction. The light signature on their screens represented a galaxy so distant that it had dethroned not just one, but multiple record holders. Before Webb, Hubble's GNZ11 at redshift 11.1 held the crown for years. Then Webb's early campaigns discovered JWST 14.0 at redshift 14.32. Now, MOM Z14, with its redshift of 14.44, pushed humanity's cosmic vision even further back in time than ever before. Webb's infrared sensors had captured photons that began their journey over 13.4 billion years ago, stretching and reddening as they traveled through the expanding universe. The telescope's revolutionary design allowed it to detect these ancient signals with unprecedented clarity, revealing details ground-based observatories could never hope to capture. Each photon reveals clues about star factories blazing at record speed in the universe's earliest epochs. Breaking the distance record should have been the headline story. But astronomers quickly realized this achievement was just the opening act. But distance was only the start. Its brightness, size, and chemistry would defy every model. The galaxy's redshift value of Z equals 14.44 meant they were witnessing the universe when it was merely 400 million years old. You'd expect a newborn galaxy, but MOM Z14 behaves like a mature system. This comparison becomes even more striking when considering what 400 million years represents in cosmic terms. The universe had barely cooled from its initial expansion, and the first stars were supposed to be just beginning their work of creating the heavy elements necessary for complex structures. Yet here was MOM Z14, displaying characteristics that suggested a level of development that shouldn't have been possible so early in cosmic history. The implications began to sink in as research teams analyzed the data more thoroughly. This wasn't simply another entry in the catalog of distant galaxies. MOM Z14 represented something that could fundamentally challenge our understanding of how quickly cosmic structures could form and evolve after the Big Bang. Scientists confronted a galaxy that appeared to have skipped several expected evolutionary stages, achieving in 400 million years what should have taken billions. The deeper they looked, the more impossible MOM Z14 became. A galaxy that shouldn't exist. What they discovered challenged every assumption about early galactic development. This galaxy exists in a cosmic period when everything should be dim and primitive. Yet it blazes across space with the intensity of a mature stellar powerhouse. The brightness readings from Webb's instruments reveal something that fundamentally contradicts our models of early universe development. Early galaxies were supposed to be faint, struggling collections of the first-generation stars. Think of them as cosmic toddlers, just learning to walk in a universe dominated by hydrogen and helium. Instead, Mom Z14 burns with the luminosity of a seasoned galactic giant, outshining objects that had billions more years to develop their stellar populations. The galaxy spans about 500 light-years across, making it remarkably compact for something producing such intense radiation. To appreciate this scale, imagine cramming the stellar output of a region 10 times larger into this relatively tiny cosmic space. The density of star formation activity within Mom Z14's boundaries creates a stellar factory operating at maximum capacity when such efficiency is impossible. This brightness carries profound implications for star formation rates in the early universe. The luminosity we observe suggests Mom Z14 is bursting with newborn stars at a pace that challenges every model of early cosmic chemistry. The processes required to sustain such intense stellar birth should have taken much longer to establish in the infant universe. Where are the massive gas reservoirs needed to fuel this stellar assembly line? Current observations fail to identify the enormous clouds of pristine material that should surround such an active galaxy. It's like discovering a bustling industrial city with no visible supply chains to support the activity. The star formation rate measured in Mom Z14 suggests the galaxy has access to mechanisms for creating new stars that operate far more efficiently than anything we see in the local universe today. This efficiency bypasses several evolutionary steps astronomers assumed were necessary for galactic development. Each measurement reveals new contradictions with established theory. The galaxy demonstrates capabilities that shouldn't emerge until much later in cosmic history, when multiple generations of stars had already enriched the universe with heavy elements and complex chemistry. But even more perplexing was what Mom Z14 lacked at its core: the missing monster at the galaxy's heart. Astronomers expect to find a supermassive black hole lurking at the center when they observe galaxies with such intense star formation activity. These cosmic monsters typically serve as the central engines that drive galactic evolution, creating the conditions necessary for rapid stellar birth. The relationship between black holes and their host galaxies represents one of the most fundamental connections in modern astrophysics. In other galaxies beyond redshift 10 that JWST has discovered, supermassive black holes actively regulate these stellar bursts through their immense gravitational influence. Supermassive black holes act as both destroyers and creators in the galactic ecosystem. They consume matter voraciously. But this feeding process generates enormous energy that radiates outward into the surrounding galaxy. This energy output creates a complex feedback system that can trigger new waves of star formation or shut down stellar birth entirely, depending on the specific conditions within the galaxy. Webb's detailed observations of Mom Z14 revealed something completely unexpected. Despite all the intense stellar activity blazing throughout this ancient galaxy, spectra show no broad emission lines typical of active black holes. The absence creates a puzzle that challenges our most basic assumptions about how galaxies develop and maintain such high levels of star formation. It's like finding a rainforest with no apex predator. Something's off. The entire ecosystem appears to function perfectly, with complex interactions and sustained activity. Yet the creature that should be controlling and shaping the environment is simply not there. This absence makes us question whether we truly understand the mechanisms driving galactic evolution. Black holes typically control star formation through powerful jets and intense radiation that heat the surrounding gas clouds. This heating process can prevent gas from collapsing to form new stars. Or conversely, the compression from shock waves can trigger massive bursts of stellar birth. The black hole essentially acts as a thermostat for the entire galaxy, regulating when and where stars can form. How does MOM Z14 sustain such remarkable stellar productivity without this central regulatory mechanism? The galaxy operates its star formation factory at maximum efficiency, yet lacks the cosmic engine to power and control this activity. Without that black hole engine, how did MOM Z14 get its fuel? The answer lies in its surprising chemistry, chemical fingerprints of the impossible. Webb's spectrograph became the ultimate cosmic detective tool, breaking MOM Z14's light into its wavelengths to reveal the chemical secrets of this ancient galaxy. Each wavelength acts like a cosmic barcode, telling astronomers which elements exist inside the galaxy and in what quantities. This process allows scientists to peer directly into the stellar processes that shaped this distant object billions of years ago. Scientists expected to find a chemically simple galaxy when they analyzed these spectral fingerprints. The early universe should have contained mostly hydrogen and helium, the only elements forged during the Big Bang. MOM Z14 was supposed to represent a pristine snapshot of the cosmic youth, reflecting the elemental composition that existed when the universe was still in its chemical infancy. Instead, Webb revealed a galaxy rich with heavy elements that simply shouldn't exist yet. The spectrograph detected powerful emission lines, revealing significant amounts of nitrogen that require complex stellar processes to create. This discovery immediately shattered expectations and raised questions about how quickly chemical evolution could occur in the early universe. Here's the cosmic alchemy problem that makes this discovery so revolutionary. Heavy elements like nitrogen are forged exclusively within the nuclear furnaces at the centers of massive stars. These stellar giants must complete their entire life cycles, burning through their fuel over millions of years before exploding as supernovae and scattering their newly created elements into space. Massive stars live for millions of years. Yet MOM Z14 shows multiple generations in just 400 million years. The timeline paradox becomes clear when considering what MOM Z14's chemical complexity means. Multiple generations of massive stars had already lived, died, and enriched this galaxy's interstellar medium with their processed elements. It's like discovering a sophisticated cookbook filled with complex recipes in a library that supposedly predates the invention of cooking itself. The chemical richness Webb detected in MOM Z14 actually matches the composition found in some of the oldest globular clusters within our own Milky Way. This similarity indicates that the early universe was far more chemically active and evolved than astronomers believed possible. What unknown processes could drive such rapid enrichment? That's what astronomers are racing to uncover. The implications suggest MOM Z14 might not be alone in defying our cosmic timeline. The search for similar galaxies has already begun across Webb's extensive survey data. MOM Z14 isn't just a cosmic oddball that formed against the odds. This galaxy represents an entire population of early objects that evolved remarkably and efficiently, completely contradicting our predictions about the infant universe. Astronomers are actively searching Webb's data for more of these impossible galaxies, and each discovery adds evidence that the early cosmos operated under different rules than we assumed. This single galaxy is forcing scientists to rewrite fundamental sections of cosmology textbooks. Webb will likely uncover dozens more galaxies like MOM Z14. And upcoming programs with the Roman Space Telescope could find hundreds of these ancient giants. Each one could reveal new secrets about how the universe truly began its transformation from cosmic simplicity to the complex structures we observe today. If you're as fascinated by these cosmic puzzles as we are, hit subscribe, because Webb's just getting started. What do you think powered Mom Z14's lightning-fast growth? Let us know in the comments. If you're as fascinated by space as we are, you won't want to miss these other videos. We dive even deeper into the universe's secrets and explore recent discoveries that could revolutionize your understanding of the cosmos. Thank you for joining us on this cosmic adventure. Stay curious and keep looking up.